Hello, everybody. Welcome. All righty. So today we're getting ready to start. We have one more minute, but we're starting a new concept, which is nuclear particles, which is probably something you've already learned in school, but we're going to go over it again. But before we begin, this week you're also going to have, you are going to have an exam this week. You have between now and then Tuesday midnight, you'll have an hour to take the exam. So does anybody have questions on how things are going or what the exam might be like, things like that?
Is the exam like comprehensive, like basically all the chapters from 1 to current, whatever?
Yeah, 2.6. Everything that we have covered, either I said, read this section, watch this video. In Zoom, we're talking about this thing. So at least 3 ways, every topic has been touched on. So if there's a section you're like, I don't remember doing 2.1, it's because we didn't do it and I won't test it. So if there's a section you're not sure about, email me and I can let you, or remind me and I can let you know. Yeah, everything we've covered, including the thing we're going to do today. Other questions? And just start talking about atoms. Okay, in this chapter 2, we start to talk about nuclear particles, and there's atoms and ions. And so an atom is something that has a certain number of protons, and it is equal to the number of electrons. And when that's true, protons are positive, electrons are negative, there's no net charge. We call that an atom. For ions, the number of protons does not equal the number of electrons.
Sue?
Yeah.
Well, we can't see your screen.
I shared my screen. Can you see it now?
No.
Oh, okay. I'm sorry. I thought I shared my screen. Let me try again.
Thank you.
How about now? Thank you for telling me. Let's see. This week, you're going to take a test. The test is going to include all the material, including what I'm going over today. What I'm going over today is not difficult, but it does have some definitions that are really important. So for this test, 2.5 and 2.6, those sections in your book are going to talk about atoms and the particles in atoms. There are 3 subatomic particles. There are protons in the nucleus that are positive. They have a +1 charge, and they have a certain mass. And then there are neutrons that are in the nucleus that are neutral. Each neutron has no overall charge. And there are electrons that are negative, and they aren't in the nucleus. They orbit the nucleus. And they have a -1 charge. So when I'm talking about atoms, I'm talking about things where the number of protons equals the number of electrons, and there's a certain number of neutrons, and they're neutral. The overall atom is neutral because all the pieces add together to a charge of 0. We will deal with ions, but we'll deal with ions next week. So all the particle counting that we're going to do today and tomorrow, and then in this week's exam, is all atoms. Atom is given a symbol, like here's carbon. And the symbol is a C. And then there's a number that goes down here and a number that goes up here. And because we're not dealing with ions, we're not going to have any charge. So there's nothing that's going to go in the upper right-hand corner. So I'm going to say symbol would be something like X. And then here we have an A, and here we have a Z. And the Z stands for, a number of protons, the atomic number. And so carbon is element number 6. Carbon has 6 protons. Every atom of carbon has 6 protons. If an atom had something that wasn't 6, it wouldn't be carbon. 6 is the number for carbon. And then up here, we have something that's called the mass number. I don't know why they couldn't pick the symbol A for atomic number. That would really have helped me. It seems intuitive, but they didn't. And then here's the next piece that is really not helpful, but is true. The mass number is not a mass. It's a counting number. The mass number is the number of protons plus the number of neutrons. That says, that looks really bad. That says number protons plus number neutrons. And so I can't tell you what mass number carbon has because there's 3 kinds of carbon. And so each of the different kinds of carbon is called an isotope. And so the 3 kinds of carbon are carbon 12, carbon 13, and carbon 14. Every carbon has 6 protons in its nucleus, or it's not carbon. But carbon 12, so this number is protons plus neutrons, this number is protons, and if I subtract them, what I get is neutrons. This is me thinking here. So 12 minus 6 is 6. Carbon 12 has 6 protons, or it wouldn't be carbon. Carbon 12 has, because it's carbon 12, 6 neutrons. And then because we're talking about atoms, 6 electrons. Carbon 13, so I'm going to look at the number of protons plus neutrons and subtract the number of protons, and I get 7. Carbon 13 has 6 protons and 6 electrons, or it wouldn't be an atom of carbon. But it has 7 neutrons. So these are 2 flavors of carbon that exist and are very stable. There is a third one that does exist but is not stable. And so we refer to it as being radioactive, which means the nucleus is not stable. It is going to change into something else. And that is carbon 14. So carbon 14 is an atom. It has 6 protons and 6 electrons. 6 protons, or it wouldn't be carbon. 6 electrons to match the protons, or it wouldn't be an atom. It would be an ion. But it has 8 neutrons. And this one is radioactive, which means not stable. So when you do the FET today, jump up to that real quick. Let's see, not today. Whenever you do the FET, the lab for this week is a simulation from the University of Colorado, and they're called PHET, FET. And there's a link that is given on the lab page, and there's also a link given on the worksheet for the lab page. But we're doing build an atom. And then I'll tell you on the video, go ahead and open up net charge and mass number and change your model from orbitals to cloud. And then under show, change it so it shows stable and unstable. And then you start putting things in. 1 proton is hydrogen. It has a charge of +1. Now I have helium. Let me go ahead and make it an atom of helium. So when it's an atom, the net charge is 0, and we're focusing on atoms. Because there's 2 nuclear particles, the mass number is 2. Let me add some neutrons. And so now the mass number is 4, because the number of protons plus neutrons, 2 plus 2 is 4. And then I can look up here in the upper left-hand corner and also see that information. So I'm going to go ahead and get to carbon. Just drag in my protons. Come on. And if I have 6 protons, it's carbon. It needs 6 electrons to be neutral. Now it's an atom. Not now. Now it's an atom. But 2 neutrons is not enough neutrons to hold that carbon nucleus together. And so it's shaking around and it has the word unstable. I'm going to continue it to add neutrons until it is stable. Okay, now it's stable, it's not shaking, and I can see the word stable, and this is the isotope of carbon that we call carbon 12, because it has a mass number of 12. And the mass number is just counting the number of nuclear particles, the particles in the nucleus. 7 neutrons, also stable. 8 neutrons, not stable. So carbon-14 does exist, and it is used for carbon dating, but it is not stable. It's going to change into something else. For counting particles, you just have to know, like, protons, neutrons, which is the atomic number. In this case, 6, the number of protons, because we're talking about carbon. What's the mass number? That's the total. So in this case, the mass number is 12, the mass number is 13, the mass number is 14. And then how do you name it? We might call this carbon 12, or we might just put the symbol for carbon. It is an isotope of carbon. And there are, oops, I got a lot going on this page. One, two, 3 naturally occurring kinds of carbon, but only 2 are stable. And why are they stable? Because they have the perfect number of neutrons, the nuclear glue that keeps those protons sticking together. Okay, so your Jamboard looks like this. Some things are super radioactive, like you can make them and they're going to degrade that minute or within seconds or nanoseconds. And then some things are radioactive, but they're not going to change very fast. And so let me show you a quick table. I'm going to do table of isotopes. This is my favorite table of isotopes. Okay, so here, this is a little snippet from the table, but it shows you, example, here's the kinds of nickel that exist. And the nickels that are gray are stable. So there are 5 isotopes of nickel that are stable. The ones that aren't white or gray, but some different color, 1, 2, 3, 4, 5, those are ones that have half-lives that range from like 500,000 years to nanoseconds. And then the ones that are white are so unstable that if you make them, they unmake themselves immediately. So the way that all these nickels vary, every nickel has 28 protons or it wouldn't be nickel. But the number of neutrons, like this stable isotope, nickel 64, has 36 neutrons. For some reason, 36 is stable. And then if I could find the whole table over here, they would have a key to tell you how unstable things are. Do they break apart in a day or in 1,000 years or in 1,000,000 years? But those are all unstable. And we can't predict what makes a stable isotope. We can only observe what actually exists. Okay, so today, this is our goal. Here I have a chart for you to fill in. If the element is mercury, this X should really be an Hg. So you would change that to Hg. And then 80 is the atomic number, and 201 is the mass number, and the number of protons is here. Yes, the number of protons to electrons on this table is always going to be equal because these are all atoms. Will that be true next week? No, next week we'll introduce ions. But yeah, you're going to fill out that table. So one last thing I want to show you is when you look on a periodic table, it looks different, and there's a reason it looks different that is important. If I was looking at carbon on the periodic table, it would look like this. And this would be Z, which is the number of protons, which is also known as the atomic number. And then this number here is not a mass number. It's an actual mass of a weighted average of all the stable isotopes. So this number here is going to be important, but we're not going to talk about it for a week or two. So when you're looking at a particular isotope, you would never focus on a number on a periodic table because it's a mixture of all the isotopes depending on how abundant they are. So it's a weighted average. So for the work that we're doing in this area, When we're talking about isotopes, this is an average. We're not going to use our periodic tables for anything in this lesson today. We're only going to look at a particular isotope that is given and the numbers that are associated with that isotope.